Yes, sir. Oh, that's just to see if you could, if you wanted to do the test, just try it. It's not for any grade or anything. This is how an at-home test like that go. You guys are my test case to see if that would work. So far, not so good.
Isn't our exam on next week?
I think so. Yeah, like next Wednesday, right? Yep. What's that? Yeah, it's next Wednesday. We'll talk about that more on Wednesday. But yeah, that was just a practice thing. Yeah, it wasn't available to anybody else. Yeah. Yes. What's that? Uh-huh. Not really. I mean, yeah, you got your, yeah, otherwise I've got 350 students, and if I have like 300 exceptions to all this, I don't have enough hours in a day to keep track of all that. So, but anyway, so there you go. I'm upset. I've got this. I have these simulations I like to run from the University of Colorado site. They've always worked before. They worked all last semester. They worked up until last week. And now all of a sudden I don't have the clearance or whatever with our IT geeks to be able to access it today. So that's got me upset. The other thing, just personal note, my dad's not doing too well, and I need to get home here pretty soon. So, and the doctor, all right, what I want you all to do, when you go to, how many of you are pre-med? How many pre-medders do I have? All right. When you become a doctor, speak clearly and say things and be punctual and talk to people, all right? So that people don't want to take you out and kick the crap out of you, all right? So anyway, well, we don't know. We're trying to figure, all right, fine, but tell me what you do know. Well, I can't do that. All right, then we got issues. Anyway, so going on, moving on. That's my own personal problem, but anyway. All right, me and the medical profession in general just kind of don't get along. Anyway, all right, let's go ahead. Let's talk about capacitance. Let's go ahead and go through the PowerPoint slide here. Slideshow, view show. Let's just start right here with capacitance. Oh, there we go. And I'm going to kind of fly through this a little bit today. We might do, I'll do some of the examples, but I promise we will do a couple of the homework problems on capacitance. I did want to show kind of the neat slide or the neat thing that we've got on capacitance. Basically what capacitors are, for the scope of this course, capacitors are a way that we store charge. They're just like batteries, okay? They're just batteries. That's measured in farads. All right, that's a new term. They're measured in farads, and usually in micro to nano to pico or pico. How do you say it? Pico or pico? What's the preferred? Pico farads, because 1 farad is huge. It's huge, okay? And basically what happens is, if you have a battery, all right, I'm going to go ahead and draw it. I'm going to draw it over here. So we'll try and draw it on both sides. Well, do they have a darn circuit here? Yeah. Let's take a look at a circuit. Where do they got a circuit drawn? Here they go. Here we go. Here we've got a circuit drawn. Now, let's take a look at what happens here. Let's take a look at what happens here with our capacitance. Then I'll go back. All right. Now, these capacitors are considered stored, are aligned in series. Okay? Those are in series. Right? Isn't that what it says? Yeah. Those capacitors should be lined in series. All right, so now what happens is, here's what happens. Now notice, these two things right here, since they're kind of separated here, the circuit's kind of broken a little bit. All right, and eventually you can discharge. Now what's going to happen, usually what you have here is you've got AC voltage vice DC. AC is what's changing all the time, okay? AC, back in black. But anyway, you've got all night long. You got, sorry, my old thrash bands are coming back to me here. All right, you got plus and minus. So anyway, we haven't done circuits yet, but I'm going to just show you what happens here. I did have a neat simulation, but it's not working today for some reason. So anyway, you get a bunch of, now, according to Ben Franklin, protons move. We know better. We know that it's electrons, free electrons, basically banging into each other. They're not really moving too far. And in fact, one of your more complicated questions you're going to get from your little questions that you have to answer on your lab is what's drift velocity. And basically what drift velocity is, how fast is that little electron moving from one spot to another before it bangs into another one and moves. Because basically what happens is, all right, let's get the big idea. I think we should do the big idea of electricity. I think I've done this before, but let's say we're all the free electrons. We're in a wire, okay? And we're the free electrons. We're the ones that are free to move about the country, all right? And somebody puts the back end of a battery over there, the negative end of a battery becomes that whole wall. Somebody opens this door, so what are we going to do? We're all going to want to run out the door. But that's really not what happens, okay? That's really not what happens. What happens is Tim Yee bangs into Sarah, who bangs into Stacy, who bangs into all the way down here to the front, okay, is what happens. And that drift from TE banging in to Sarah is called her drift velocity, all right? And so that's what happens. Now, what Ben Franklin said happened was protons move, and so we've got this the general model or whatever, by convention we'll have the protons move. So we got this battery. So I've got this proton moving around here, and it comes here and it starts to collect on this plate. All right, it starts to collect right here on this plate. Now what happens? If I get a bunch of protons getting charged up over here, what happens on this plate right here? A bunch of electrons get stored up here. So we get a bunch of electrons stored up. So what happens to the protons? They come down here. And then what happens? A bunch of protons start building up here. A bunch of electrons start building up here. So that pushes these protons down here. The bunch of protons start building up here. A bunch of electrons build up here. Protons then come around here, are attracted to this negative end. What happens in a battery? It does work. Takes that proton, moves it over here. That's technically not what really happens, but we can visualize that that's what happens. You got this little chemical. In fact, in one of those sites I showed, they look like little fairies. Come over, grab the proton, move it over here, set it on this positive plate. It doesn't want to stay there. Goes around again. That's current. So it all collects up here, collects up here, collects up here. So all the charge that's collecting up here, notice what it says when they're in series. Q1 equals Q2, which equals Q3. So, what you don't know, so that's how capacitors get charged up. All right? So, eventually what happens is you can discharge them, you can discharge the capacitor, or it gets so strong right here that it busts through the air gap that's in there, which a lot of times we put a dielectric in there, which we're going to talk about. I've got to go back a few slides. I kind of started at the back end of where the chapter starts to talk about capacitors, just so you'd learn about it. So a capacitor means a capacity to store charge, which stores energy. That's the whole idea behind capacitors. Is you put them in circuits because the big idea behind circuits is we want to be able to control that amperage so it'll do work for us and not just willy-nilly run around and do things. So that's why we put resistors in there. That's why we put capacitors in there, and we want to control that amperage that goes around in there. So let's back up a little bit and let's look at what capacitors are. All right, capacitance. Okay, so they don't even give the equation for capacitance? It's annoying. No, they don't. All right, but that's all right because we got it. Here's the equation for it. The charge in a capacitor, Q, is equal to the capacitance times the voltage. Q equals CV. Okay? So Q equals CV. So the energy in a capacitor, since energy is equal to QV, right? Since energy is equal to QV, and the work done to charge up that capacitor, because work has to be done by that battery to push that charge to store up that capacitor. The work done is the average voltage. The average voltage that was pushed across there. So we've got, and when we substitute V, remember Q equals C times V. And so when we substitute V with Q over C, we get Q squared over C, 1/2 Q squared over C. Or if we substitute Q for CV, we get 1/2 CV squared. Both of these are equivalent because remember, so far we know, barely we know, because there's so many formulas thrown at you in E and M and how things work. You may have forgotten, energy is equal to charge times voltage, QV. Okay, and so the energy that's stored in the capacitor is equal to the average voltage, QV. Just like when we found 1/2 mv squared for the kinetic energy, we didn't use mv squared. We used the average velocity, so we got 1/2 mv squared. And thanks. So anyway. So Q times V is the energy, and so the energy stored in the capacitor are these two expressions right here. Okay? All right. Now then, dielectrics. Okay, so you already saw a parallel plate capacitor, and that's pretty much what we're going to deal with in this class, our parallel plate capacitors, all right? And what we do is to drop the voltage, but to increase the energy, or to, I'll get to that in a minute, but is another word for an insulator. A dielectric inside a capacitor increases the passive energy storage by an amount carried per. I knew we'd put them in there for a reason, and I knew I'd find it somewhere. So there it is, real big on your slide, where we put those. Now remember, if you look at these things, you go, wait a minute, these things are all great insulators. You're right. But they increase the storage capacity of the capacitor, and each one of these has a dielectric constant of K. Now this gets confusing because we use that K, which is 1/4 pi E naught, right? That's our K, but this is the real K that's used for a dielectric material that we will look at here in a minute, all right? Now all of these guys are insulators. Okay, so how the heck does an insulator, why would you put an insulator in there if you want to increase storage? Well, here's why. Because what we're going to do is we're going to decrease the electric field. Okay? We're going to decrease the electric field, but keep the voltage the same, and so therefore it'll increase the energy. So let's take a look at how the heck that happens. All right, so here's what happens. Here comes this dielectric. Now notice, it's all jumbled up here. It's an insulator. Okay? But still, what happens is, and you got this initial electric field here, and the voltage equals E naught times D. Okay? The voltage equals E naught times D, and so it comes down here, but notice what happens when it starts entering that electric field. It becomes polarized. And so you've got this charged capacitor with a dielectric inserted, and so you got all these polarized atoms in there, and they're all lined up. Okay? And so what happens, now look what happens. The electric field comes from the positive and goes towards the negative, right? So it comes here and goes to the negative. But you also start to get this you also start to get this cross-electric field coming this way inside the dielectric. So it's taking away from the initial electric field that's going through there. Because remember, we can add electric field just like vectors. All right? So if you got one coming this way and one going that way, that decreases it. So now the electric field in here is decreased, and the effect on the electric field and the voltage, it now drops the voltage inside that parallel plate. Okay? All right. Okay. So this allows for it to stay in a larger electric field for the same potential difference. All right, so we can it increases. Now, how does that work? All right. You might be wondering, going, now wait a minute, what just happened? What just happened? All right, so what happened here was we decreased notice the new electric field is decreased. So with the same potential difference, in other words, the Q naught and the original Q here in the thing, we can get more of an electric field in there because we decrease the original one, so we can add more charge and we can store up more energy in there. Okay? All right. Good. Okay. So here we go. Capacitance. The capacitance of a capacitor containing a dielectric is increased. Okay, so we increase the capacitance by that now this is not the K, this is not 1 over 4 pi E naught. All right? This is the this is that dielectric constant. So the new capacitance is equal to K times the original capacitance. And I hope they gave a formula for capacitance. I got one. Okay. All right. Oh, here's what I was talking about. Yeah. All right. So here we go. Okay. Right. Hold on a second. I'm taking a look at this thing. Okay, now look what happens. If we disconnect the battery, if we got it put in here, disconnect the battery, notice that since we've disconnected the battery, the charge isn't going up at all. The charge isn't going up at all. But when we insert that dielectric, what happens to the voltage? It decreases. Okay? It decreases. All right? But if we leave it charged, if we leave it hooked up to the battery, now this time we keep adding charge to this thing, keep adding charge and adding charge to this thing, and so that when we add the dielectric, notice the voltage stays the same because it's still connected. The voltage stays the same, but the charge goes up. All right? So the ratio of charge to voltage increases. Here the charge stays the same, voltage decreased, charge increases, but the voltage stays the same, so therefore we're allowed to increase the energy. All right. It's able to store. Okay. All right, so now we got to this thing. Let's take a look at what do your problems look like? What are we actually talking about here? And plus, I don't think they gave you any good formulas here to work with. Did they? Nope, because that just gets into the review. Okay, so the slides don't help us much there, but I brought some handy dandy stuff that just might. So let's go to the dot cam here for about the next 20 minutes and take a look at some of those things that I have figured out. Okay. Hopefully it won't be as confusing as those slides were. All right, in series, that's a blank sheet. All righty. Okay. Did the dot cam come? It did. It did. The dot cam came up. Good. All right, so here we go. Now, one of the problems in the book, let's take a look at how large is a farad. All right, so here we go. Let's take, first of all, let's do a few things here. All right, let's do a few things here. Let's take this. We know this. We know that the charge Q. Oh, that's not gonna work. What do I need to do? Turn the lamps on, right? That help? What's? Uh-oh, that's worse. That's not any good. That one works best. Okay, so we've got Q. All right, Q is equal to your capacitance times your voltage. All right. Now, for parallel plates only, we found this. In fact, it was one of your problems earlier, I think from chapter 15, where E is equal to 4 pi k. Now be careful. Q divided by the area of the plates. All right? All right. And then, hold on a second. Let me flip the page here real quick. Then we've learned this, that V is equal to E times D. Okay? Voltage is equal to the electric field inside a parallel. Now, this is only good for parallel plates. E times D. And so, we've got 4 pi k q over A times D. Here's a derivation. Nothing like a good old derivation to start any Monday. Let me turn off these lights. This might help a little bit. Keep you all in the dark. You're in the dark anyway because you can't see what I'm doing. All right. There we go. That's a little better. All right. Okay, and then what we do is we know this. We know that C is equal to V over Q. So basically what happens is you do a little bit of algebra there, and you wind up with this. You wind up with C is equal to permittivity of free space times A over D. I'm looking on page 576. There you go. There's your capacity. Now this is for parallel plates only, and that's the only geometry we're going to use. Anyway, yes. Yeah. There you go. Good fix. It's kind of damn having. There we go. C is equal to Q over V. Duh. C. Why don't we divide V by both sides? Good catch. Thank you. Thank you. But this does work out. Trust me on this one. We'll wave the magic algebra wand, okay? And then it asks this. I got a question for you. What happens to my capacitance? So now looking at this, this kind of makes sense. What happens to my capacitance if I increase the area on the parallel plates? What happens to my capacitance? It should increase. What happens to my capacitance if I increase the distance between the parallel plates? It decreases. It decreases. But what happens, here's an interesting question. Keeping this in mind, that the voltage equals E times D, as long as I can keep E pretty constant through the plates, this is kind of an interesting thing. What happens to my voltage in parallel plates if I increase the distance between them? Does it go up or down? It actually goes up. People think, oh, wouldn't it go down? No, it actually goes up. If we can keep this electric field the same, the voltage actually increases when I increase D. Okay. So, in other words, if I disconnect, so that's one of the things. Here we go. I knew I could explain this much better once I got into this thing. Okay, so now, if the amount of charge stays the same, in other words, if I unhook something, if I unhook the parallel plate capacitor from the, this explains it much better. If I unhook the parallel plate capacitor from the battery, that means Q has to stay constant, right? Q has to stay constant. So, if I add a dielectric to it, what happens to C? Does the capacitance increase or decrease? It increases. It increases. So if C increases and Q stays the same, what happens to my voltage between those plates? It decreases. That's what that slide was trying to tell you. All right, so now you can see, you go, oh, okay, well that makes sense. Cool. All right, that makes sense to me. Now then, what happens though if we leave that capacitor, that parallel plate capacitor hooked up to the battery? What happens to the voltage in this case? It remains the same, and when I put my dielectric in there, what happens? So if V stays the same, what happens when I put my dielectric in there? C goes up, so therefore what happens to Q? It increases. All right, so now it makes sense. There we go. There we go. All right, and if I leave the battery hooked up, that's one thing I wanted to. That's why I wanted to have my nice little simulation so you can see what happens. The charge keeps crowding over there, keeps crowding up there, and the Q goes up. Eventually what happens, now think about this. Let's say I've got a capacitor, a parallel plate capacitor, just try to imagine, I've got a parallel plate capacitor hooked up to a battery, and I've got a little bit of resistance in there to keep it from burning up completely, because what happens if you don't have any resistor in a wire, you just have a battery hooked to it, wire catches on fire because you got no resistance. It's kind of a bad thing, all right? Can happen, all right? But, so we put a little resistor in there. Now what's going to happen to that parallel plate as that charge keeps going in there? Eventually what's going to happen? It's going to stop. It's not going to have anywhere, it won't be able to take any more charge. Okay, because it'll get all backed up and everything will stop flowing. That's why we usually hook them up to AC currents so that it can be discharged, so it bounces back and forth all the time. All right, so there we go. Now that made sense. Okay, good. Now, here we go. Let's take a look at a good old defibrillator type thing, because it's basically a capacitor. All right, and guess what? Your body becomes a dielectric that you put between the plates of the capacitor. Boom. All right? And you close that circuit. All right? Now then, so here's what happens. It says, during a heart attack, the heart can beat in an erratic fashion called fibrillation. One way to get it back to normal rhythm is to shock it with electrical energy supplied by a cardiac defibrillator. Okay? All right. About 300 joules of energy is required to produce the desired effect. Typically, a defibrillator stores this energy in a capacitor charged by a 5,000 volt power supply. Okay, so 5,000 volts is our power supply. What capacitance is required? What is the charge on the capacitor's plates? Remember, the charge on one plate is positive and the charge on the other plate is the same amount that's negative. So, this started out, it said that the energy was equal to 300 joules. Energy was equal to 300 joules. Now, voltage was equal to 5,000 volts. Okay? Two questions it asks. What's the capacitance of this thing? And what is the, what's the capacitance? What is C? And what is Q? So, well, we can jump right in and go, all right, well, Q equals CV. Uh-oh. I ran into a problem. What's my problem? Two unknowns in one equation. I'm dead in the water. Or I can just make up any answer. In other words, I got infinite solutions. This is great. Any answer should work. All right, but that's not what we're after. All right, so is there any way to get from here, from joules, can I do something with that joules information? Yeah, what is it? Yeah, we can use the, okay, joules, energy. What does energy equal? As Rashid is dying to find the other equation, what is it going to be? Q times V, right? Ha-ha! We can find Q because we've got the energy. So we know that U is equal to Q times V. And so we got 300 joules divided by 5,000 volts is equal to whatever that comes out to be. They give me the answer here, which is good. 0.12 coulombs. That's a lot of charge. 0.12 coulombs. Okay? Now then, hey, now that I know that this is 0.12 and I know this is 5,000, I can figure out the capacitance. Notice it's going to be pretty small because I got 0.12, which is 1.2 times 10 to the negative 1, divided by,
Professor,
yes?
did you have to change something on that? Because I got 0.06. Not 0.2. Like, did you have to convert the 300 into like 3,000 into 5,000 to 500?
Oh my. Where's my geniuses in the back? What did you just say? You had to do what? 1/2, right. What did I spend the first 8 minutes of class talking about? Dummy, I should have made this 1/2. My fault, my mistake. Of course you got 0.06 when you did it this way. Because if you just look at this, 3 divided by 5, or 30 divided by 5 is 6, so it's got to be a 0.06. I knew I did something wrong, because remember, it's the average voltage, all right? It's the average voltage, 1/2 QV, so we get 600. There we go. Divided by 5,000, that's 0.12 coulombs. Thank you. Good question. Good question. No, you hadn't lost your mind. I had. All right. See, anything else that I've screwed up here? Royal. No, we're good. So we got 0.12, so now we can figure out what the capacitance is. The capacitance, of course, would be 0.12 over 5,000. Notice it's coulombs per volt is our capacitance. This is coulombs per volt. And volts are energy per coulomb. So is in farads, and that winds up to be 2.4 times 10 to the negative 5 farads. Or, as they said, 24 microfarads. I don't like it when they do that because I have trouble with sliding my decimals around like that. So if I take this and go this way, oh yeah, it becomes a negative further. All right. So it came out to be 24 microfarads. So actually, so farad capacity. I'm going to bring in one of these days. Wheeling it over here is kind of difficult, as Tingy and Hal can tell you about wheeling video equipment around. We're going to bring over our can crusher. I don't know if you've ever seen that thing work. But basically, it's got a 0.75 farad capacitor in it. Stores up a bunch of charge that eventually stores up in these two metal balls that hop over like lightning into another circuit and go around in a circle. Creates a huge magnetic field, which creates a huge force. Current and magnetic field that's perpendicular to it creates a huge force, and it smashes a can. It's pretty cool. But anyway, we'll get to that when we get to current. All right, now let's do one more. All right, we've kind of explained dielectrics there a little bit, best we could. We'll do some problems where we mess with the dielectrics there some. But first, what I wanted to leave you with is, let's look at charging something in series and charging something, capacitors in series and capacitors in parallel. And let's figure out what they're going to be, how to do those problems. Because I gave a couple of those problems too. So, when you come back on Wednesday, if you do come back, anyway, if you come back on Wednesday, what we'll do is we'll look at a couple of your capacitor type homework problems. I started one of them and I was like, oh wow, it's got like 19 parts to it, and I think it was your problem number 4. I was like, and it's had some algebraic manipulations, and I just wasn't in the mood, so I said, forget it. We'll look at it before class on Wednesday. All right, now, if I have capacitors in series, let's just take a look at capacitors in series. Here's a capacitor, here's a capacitor, here's a capacitor. Here's my voltage. Okay, and here's my plus, minus. All right, and here's my voltage. Okay, now then, I think one of the big things that I haven't taught you yet, that I haven't beat into your head yet, which I should have from day one, is that charge, like energy, is constant. All right, there's only so much charge in the universe. In other words, it's conserved. All right, so if I start off with the little chemicals there in my battery can produce so much charge or voltage, that's how much charge is going to be in this problem. All right, and when those coulombs when those little electrons start flowing, well, actually by convention, thank you, Ben Franklin, by convention, when those protons start flowing, which don't. It's actually electrons going this way, protons going this way. It's the same, works out the same way. But anyway, as they move around there, charge is conserved. All right, so if this is a 12-volt battery, this is a good old 12-volt battery. I've got my capacitor 1, got capacitor 2, capacitor 3 here. If I put a voltmeter, in other words, if I put a voltmeter here and here, where I'm going to find the potential difference between here and here. Now what's going to happen is, I'm going to get a bunch of positive charge, is going to flow up through this way, collect up on this plate, negative charge is going to collect over here, and then the positive charge that's, or the negative charge is going to, the positive charge is going to get pushed away, and so it's going to be negative charge up here, and so these positive charges are going to collect down here, negative charge here, pushing away the positive charge from this plate is going to push away that positive charge, boom, it's going to collect here. Now, the voltage is here. If I put a thing here, I'm going to have a V1, I'd have a different voltage here, and I'd have a voltage here. But, now I haven't really taught you this yet, but what do you think V1 plus V2 plus V3 add up to be? 12. There you go. Very good. Okay? And we also know that Q is the same on each one of them. The charge Q is the same on each one of them. And we also know this. We know that Q, and I'm going to be real careful. Don't check me. Make sure I do this right now. I know that Q is equal to CV. So, if the charge is the same in each one, so that Q1 equals C1 times V1, Q2 equals C2 plus V2, and Q3 is equal to C3 V3. All right? And I know that all the charge is constant, so the total charge in the system, Q equals Q1 plus Q2 plus Q3. And so I know this. I know that V is equal to the total charge Q times the capacitance. Uh-oh, did I screw this up again? Yeah, I did. I know that Q is equal to the C times V. Okay? Goodness gracious. Yeah, C in series. That's what that CS stands for. Q equals CS. Ignore this guy. I'm having algebra problem issues today. Okay? And times the total voltage. Q times the total voltage. All right. Did I screw this up again? Q equals CV. That's right. That's correct. Yeah, so this is still right. Q equals CV. Whew, scared me. That's the total Q. That's the total charge Q is times CV. And that's the total voltage. So if I take each one, C1 plus V1, C1 plus V2, but I'm not even going to mess with it. I was going to tell you. This is how you solve it. You go 1 over CS is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Okay? Now then, does that equal 3 over C1 plus C2 plus C3? What? This Crunchmeister would have a field day with you. No, you can't do that. It's really annoying to do this. All right? To actually do the algebra to figure this out. So, but usually what's going to happen is you're going to be told what the 3 different capacitors are, okay? And you'll just do 1 over the first one, plus 1 over the second one, plus 1 over the next one on your calculator. Then when you get that answer, you're going to get hit x to the minus 1 because you cannot do this. This is an illegal move. You can't do this. That's illegal. Can't do, that's not true. Right? You can't do that. That's the one algebra thing I do know today. All right? You can't do that. So, if you're trying to find something in series like that, so here's a typical question. They said, given 2 capacitors, one with a capacitor of 2.5 microfarads and another with 5 microfarads, what are the charges on each and the total charge stored if they are connected across a 12-volt battery in series or in parallel? All right, so here's the question. Now, if they're in parallel, so I'm just going to leave you with the equations today, then we'll solve them tomorrow. All right, so let's take a look at, first of all, capacitors in parallel, which would look like this. And here's the voltage. Here's C1, C2, C3. Now then, when things are wired in parallel, the reason we wire things in parallel is what we want to do is we want to make it so that the voltage, we wire them so that this voltage, if this is 12 volts, what do you think the voltage difference is between here and here if they're in parallel? Don't know? By definition, it'll be 12. That's what you're doing when you're measuring them in parallel. So each one of these voltages, right here, each one of these voltages would be 12. Okay? If this happened to be 12 volts. Because another way to think about it is wiring it this is what you've done is you've wired it this way. This is plus, this is minus, this is my voltage. Then I've done it like this. Put another wire in there. And then put another wire in there. There we go. These 2 diagrams are the same thing. Okay? These 2 diagrams are the same thing. So, Of course, this is pumping out 12 volts to this wire, pumping out 12 volts to this wire, and pumping out 12 volts to this wire. Okay? And so the nice thing about this, about capacitors in parallel, okay, well, let me put that then. The voltage here, V1 equals 12. If this equals 12, V2 equals 12, and V3 equals 12. All right. The nice thing about figuring out the capacitance when things are in parallel, piece of cake. And then we'll have time to do this one little example. Then we'll look at your homework problems tomorrow, Wednesday. So is this the capacitance in parallel? C1 plus C2 plus C3. It's great. It's a way to increase your capacitance too. Most of the things in your house and in buildings, for the most part, are wired in parallel. And the reason is, if you're on a series circuit, that toaster blows. If you're in series, like here, if you're in series and the toaster here blows or something, we'd actually have a resistor there instead of a capacitor. But if toaster blows, guess what? Everything on that circuit goes out. All right? So that's why we wire things in parallel. All right, so let's take a look at that one problem real quick. We got about 4 minutes. We can do it. Okay? It says this. Given two capacitors. First one, C1. They told us what C1 is equal to. 2.5 microfarads. C2 equals 5.0 microfarads. All right? So what we need to do is they want us to, V equals 12 volts. The overall voltage is 12.0 volts, or do they say 12? They say 12.0. This is 2.50. This is 585. All right, now then. So they want us to do it in series. They want us to figure out Q in series. So Q is equal to CS times V. Okay? What we're after is we want to find out what the coulombs are in series. So we've got to figure out what CS is. Well, this isn't too bad. CS, 1 over CS, is equal to 1 over 2.5 plus 1 over 5.00. And this is in microfarads, so I can leave it as microfarads. So to add these two together, well, basically, here's what you do. Here's the way I do it. I don't do any algebra anymore. I just take 1 divided by 2.5. That equals 0.4. So 1 over CS equals 4 over 10 plus 5 over 10, or 2 over 10. And so 1 over CS is equal to, now I can add them, 6 over 10. So CS then is equal to 10 over 6, which boils down to, I'm even afraid to do that one in my head. See, I just screwed it up. It's about 1.7 microfarads. So, to find the total charge would be 1.7 times 10 to the negative 6 farads times 12 volts. And that came out to be no, it's small. That's about approximately, if I'd have done it right, it would have been 2.0 times 10 to the negative 5, right? Coulombs. All right, now, if they're in parallel is real easy. You just add them together, okay? Just add them together. And so it comes out to be 7. So you increase the capacitance quite a bit. All right, you may go. I knew I should have gone to the algebra part first.